Welcome to the talk on range adapters 5 years after C++20. I've already been told that we're not actually after C++20. It sounds like C++20 is over, although for a lot of people it's just getting started. But I do think that we've had some time now to reflect and see the impact of some of the changes that came with C++20. And while this talk is called Range Adapters 5 years after C++20, it's actually more generally about ranges since C++20, and this is the overview of my presentation. I'm going to begin with an introduction. We'll then dive into the core ranges concepts, and then discuss especially indirections and lifetime issues, and then finally come to range adapters and end with a small summary. A couple of words on myself. I have a background in bioinformatics. I did a PhD here in Berlin and also wrote a book on performing certain bioinformatics stuff with modern C++. I'm an irregular attendee of the ISA committee since 2018. And mostly hang out in Library Evolution and the Ranges Study Group. I currently represent Iceland on the committee due to a previous job that I had in Iceland. And nowadays I work for DeepL, which is one of the biggest AI companies in Germany, maybe even in Europe. We're mostly famous for doing machine translation, but we've recently also announced agentic AI and a lot of other great AI things. As always, a big disclaimer, all the views expressed in this presentation are my own and not my employer's. Why this talk? If you hang out on Reddit, I don't hang out on Reddit, but a lot of C++ programmers apparently do. And also quite a few committee members hang out on Reddit. And if you go to Reddit and look for ranges and views, you will find lots of threads of people that are confused or angry or upset. And you will even have threads where different committee members are like upset with each other or get into very strong arguments. And I found this just like randomly picked one post of someone saying, "Oh my God, this issue is a real war zone, and I'm not even sure I want to pick a side. I'm not sure I want to spend the time learning ranges anymore." And that's of course not something that we want as the result for ranges. And I think, I mean, this is very anecdotal, it's one person saying this, but I do think it shows that there is controversy around ranges. And also, even like today, if I open my mailbox sometime, you will see that there is like the reflectors, the mailing list that we have in the committee. Sometimes there will be a thread on something, the broken filter view, and it has 200 messages, and you're like, wow. Why is this still so controversial 5 years after we standardized it? And that's why I want to give this talk, because like if we look at ranges, they were probably the largest addition to the standard library ever. And people really have different expectations of what this machinery is supposed to do. Both users have different expectations, but also committee members. And of course, as with all things in hindsight, I think we would probably do some things differently. But this is C++. Everything that we do is there to stay. So I think part of the whole discussion also needs to be making peace with certain design decisions. I think a lot of the controversial aspects become visible on very specific examples, and then people tend to try to fix these very specific examples, but not really look at the larger picture. And then sometimes, while fixing these small examples, we end up making the large thing even worse than before. That's something I want to also show in this presentation. I want to kind of zoom out and discuss a few things that I consider part of the big picture. Of course, we will look at like certain examples as well, but then always try to like understand why was this made in this way, and give you pro and con arguments for certain design decisions, so you can make up your own mind whether you think it was smart that we did it that way, or maybe it wasn't so smart. I will sometimes make some generalizations that are not 100% accurate. So if you're like very deep into this, you might have like this, oh yeah, but there's an exception to this. Yes, there are lots of exceptions to almost all things, but like I said, I do want to focus on the big picture. Before we dive into the actual design space, I want to say that I think range adapters and views are really cool stuff. If you look at this code example, it's a snippet of code that you pass some text to it, and it will like split the text into words, transform the words to uppercase, filter out short words, and in the end, print all the words that are longer than 4, which is an arbitrary choice. And what I think this example shows, I've added comments for those of you who haven't worked with ranges much, so you see which of the range adapters implies which kind of transformation. And what I want to say is that I think this is a huge progress to what we had before. Imagine how you would solve something like that without range adapters. You would have nested for loops, you would have temporary variables, you'd be invoking find algorithms, you'd be doing all these things, have lots of local state, and this is very descriptive. People, when you read the code, you understand what's going on. There are no dynamic memory allocations happen here. There are like no loops, no temp variables that you need to take care of. And I think while there are a lot of things where I will also say I'm not happy with how they went, please keep this picture also in mind because it is cool stuff. A quick introduction into iterators. I hope most of you know the basic of iterators because otherwise it's going to be hard following the presentation. But here is the really short summary. This is how interfaces somewhat looked earlier. They didn't have the auto because auto is also new, but this is a find algorithm. You pass it an iterator and a sentinel into a range and some value, and then it returns the iterator of the first match, basically, the iterator pointing to the first value that is identical to the parameter. That's the abstraction of choice since C++ 98, and iterators in that sense are a generalization of pointers to begin and end of a collection. Nowadays, that's kind of a new thing, since the end of the collection, the so-called sentinel, can be of a different type. The proper way of saying this today is the iterator-sentinel pair. So it and sen are the iterator-sentinel pair. I will often just say the two iterators because it's shorter and simpler. So when I say the iterators, I mean the iterator and the sentinel of a range. This is what the newer interface could look like. You see that below. Instead of taking 2 arguments to the iterator and the sentinel, it takes 1 argument to the range itself. Okay? So before we had 2 arguments, now we have 1 argument. The nice thing about this is we can just pull out the begin and end out of the range and then invoke the previous argument. So we have some backwards compatibility there. This is the new abstraction for algorithms in C++ 20. A range is a type where begin returns an iterator and end returns a sentinel for that iterator. In a lot of types, iterators and sentinel will actually be the same type though. Yes, there's a question.
Very tiny question. Why did you pass the range by forwarding reference? And not by value. That's the question.
Because a range can contain values, and if you pass by value, you'll be copying those. But we will discuss copy semantics, reference semantics, all these things in detail, and we will return to this example. So maybe the question will be answered then. If not, tell me, and we will get back to it. I will have these slides in the presentation that have the Space Invader at the top, and those slides are design decision slides. And they will always have what the status quo in the standard is, and then pro arguments and con arguments for how this was done, kind of to give you some arguments of like, why is this a good or a bad decision, and to give you the tools to make up your own mind. This is kind of the first design decision in the whole ranges field, is whether we want to base ranges on iterators or not. And the pro arguments for making ranges be based on iterators is that we have backwards compatibility to interfaces that used those iterators before. So if you have a range and you need to pass something to an interface that expects iterator and sentinel, like this one, you can just pull out begin and end and use the old interface. It also works the other way around. So if you have an iterator and sentinel, but you have an interface that expects a range, you can just take the iterator and sentinel, put them in a std ranges subrange, and pass that on. So this design decision allows a lot of compatibility, and it's a well understood and established design. Counter arguments for doing this is that we inherit some of the limitations of the previous design. In particular, iterator design for ranges means that going to the next element and reading the value are two separate operations, and there are some ranges, we will see later, where this is not ideal. However, most of the ranges libraries out there in the wild base their design on iterators. I think ThinkCell's library is an exception, I'm not 100% sure. But going forth in this presentation, we will always assume that iterators are the basis of ranges designs. Let's dive into the core concepts. The core concept at the root of all ranges things is the range concept. Std ranges range. It requires that you can call begin on the range and get back the iterator, and that you can call end on the range and get back the sentinel. I have this abbreviation here. Keep this in mind for a lot of slides. I abbreviated the namespace to SR just for space reasons. Yes, anyway, nothing is promised beyond these things. There are like very, very minor promises we will see later, but the general thing is std ranges range implies that you can call begin and end on it. That's it. So containers are ranges, like std vector int is a range, and std ranges begin just forwards to the member begin function. Okay? However, an iterator sentinel pair on its own is also a range. So I've mentioned std ranges subrange. That's basically just a std pair of the iterator and the sentinel. It also has a begin and end member function, but like conceptually it's just a pair. And this is something that has lots of implications, right? A range is a container, but a range is also just a pair of two iterators. Subrange is not a great name. Like often it refers to actually the whole thing, but you can use it to refer to the subrange of something, and we didn't have a better name, so it ended up being called subrange. The further range categories. On the left, you see the iterator categories. I hope most of you have seen those iterator categories before. I will quickly go through them. On the left, you have the iterator categories. On the right, you have the corresponding range categories. Input iterators allow one iteration over a range. Forward iterators allow iterating over the range multiple times. Bidirectional iterators allow going backwards in the range. Random access iterators allow jumping to elements in constant time. And contiguous iterators promise you that the elements are stored adjacent in memory. You can map standard library containers onto all of these. So the std forward list is a forward range. The std list is a bidirectional range. The std dec is a random access range. And a std vector is a contiguous range. All of these concepts refine the concept above them. And the range concept just implies the corresponding iterator concept on the iterator. Okay? Important, the range category concepts add no requirements beyond the iterator sentinel requirement. What does that mean? Have a brief look at this code. It's a function that sums up the elements in a range. Now, you see that the for loop in there is not a range-based for loop. I'm doing that on purpose because I think you will still often see this kind of code, and there are situations where you want this kind of code, where you use indexing into the range. There are some concept annotations up here. I don't know how familiar you all are with those. So we're enforcing that the argument is a random access range. We're also enforcing that the element type is an integer type so that we can actually sum it up. And importantly, we're also requiring that the range is a sized range because we're calling std_range size on it. And the random access range does not imply sized range. As I said, random access range concept just promises that the iterator that you get out of it is a random access iterator. No promises beyond that are given on the range. But this example is still under constraint. And unless you've dived deep into ranges things, you will not see this, and it will probably be surprising. And that is, in the body of the for loop, we're invoking the bracket operator on the range, and random access ranges don't even promise you a bracket operator on the range. They only promise you that you get a random access iterator, and on the iterator you can then use the bracket operator. But there is no guarantee that the range itself has a bracket operator. Now you might think, wow, what like a nitpicky thing to think about. Like, no sane person would make a random access range that does not have a bracket operator, but you've not estimated the deviancy of the committee, because we're actually shipping multiple random access ranges in C++26 that either do not have a bracket operator, or where the bracket operator does something different from the bracket operator on the iterator. And there are reasons for this, and we're not going to dive into those reasons here. Std flat set is one of those containers. It's stored like a vector internally. And so it's a random access range because you have contiguous storage. But since it's a set, they didn't want you to have a bracket operator on it because it would look like a lookup, so it doesn't have it. Okay? The take-home message here is the range category concepts only mandate things relating to the iterator and not much else. Multipass guarantee is something that differentiates single-pass iterators, the input ones, from forward iterators. So if you remember this table, the first line is single pass, everything below that is multipass. What does multipass mean? Multipass implies several things that are not immediately intuitively connected to this, but that are implied by the concept. So a forward iterator can be default constructed, it can be copied, and it can be compared against self. Those things we subsume in the std regular concept. There are if you have two forward iterators, they form a range. And if you increment one iterator, that does not invalidate another iterator. And if you create copies of an iterator and independently increment them, they will yield the same values. All of these things might seem very unsurprising to use, and you might be wondering why I'm even highlighting this, but we will see that in a second. On top of that, for multipass ranges, begin returns a forward iterator. Those are the things we get implicitly. And begin can be called multiple times. And begin does not modify the range. Furthermore, the complexity of calling begin repeatedly shall amortize to O of 1. So if you do lots of calls to begin, in general, these calls should be O of 1 complexity. To summarize this whole thing, you can iterate over the range multiple times and will always observe the same elements. That's the multipass guarantee. If you have a forward iterator or a forward range, you can iterate over it multiple times. You will always observe the same elements. Here are some examples of this. You can create a vector. You can create multiple iterators into the vector. You can copy the iterators. If you increment the iterators separately, they will still compare equal. None of this is really surprising because all containers are multipass ranges, and this is probably what all of you have been used to since forever. It's important to note that the iterator is an observer to the range. Right? The iterator, you create it from the range, you can use it to look at the range, but the iterator itself, if you create it, it doesn't change the range. If you increment it, it doesn't change the range. If you deref it, it does not change the range in an observable way. And this half sentence will play an important role later. Anyway, these properties most of you expect, not surprising. A few things that might be surprising are that std forward range does not imply regularity. So the forward iterator implies regularity on the iterator, but the range concept does not imply regularity of the range. Furthermore, although, as we've just said, iterating is observing, there's no promise that a constant is also a forward range. That might be surprising. All the containers that we know, if we have a constant of the container, it's still basically the same thing. You can't change the elements, but you can still iterate over it. This is not promised by the forward range concept. Okay, what's the opposite of forward ranges? The opposite of forward ranges is single pass ranges. Those are the ones that are input but not forward. For single pass iterators, it holds that they don't provide the multipass guarantee. So all the stuff that I just told you is not promised by single pass iterators. They're not required to be default constructible, copyable, or comparable with self. You may need a special type as a sentinel to actually form a range. And importantly, if they are copyable, incrementing one iterator may invalidate another iterator. The respective properties of the single pass range is that begin returns a single pass iterator, but it might be undefined behavior to be called begin more than once on the range. This is not true for all single pass ranges, but in general it is allowed. So if you work with single pass ranges in general, you need to assume that calling begin more than once is undefined behavior. In the cases where it's safe to call begin more than once, no promises are made about complexity. So in general, for single pass ranges, assume that you can call begin once and that the range is exhausted when the end is reached. This is something, if you're like used to programming in Python, you have generator expressions, and if you go over the generator once, at the end of it's empty. This is the kind of the behavior that is implied for single pass ranges. There are no single pass ranges in the pre-C++ 20 world, and there are only few single pass iterators, and the stream iterators are one of the examples. And I think if you think about this example, some of the things I said on the previous slide make more sense. Right? We can create multiple iterators on the stream, but if we increment one iterator, that pops characters out of the stream. And that means the state of the stream changes. And if we had previous iterators that also pointed into the stream, these are now invalid. And if you're a physicist, you might call that spooky action at a distance. And it's one of the reasons we've made the new single pass iterators all move only, so it becomes harder to create such situations. However, C++ 20 also introduces std generator, which is the coroutine-based range. And this is always a single-pass range. So I think we will see a lot more single-pass ranges out there in the wild in the future, because std generator makes it really easy to create ranges. And Nico has a talk on this tomorrow. I recommend checking it out. Ah, today, okay. Well. It's Std generator is 23, okay. Here's one example where you have like an infinite range, which is like all the values from 0 to until you run out of size t. Anyway, let's sum up. Single pass ranges. Single pass ranges change state during iteration. The iterators are not observers, they modify the range. It's natural for these ranges to not always be default constructible, comparable, and or copyable because they contain resources like a coroutine, like a stream, possibly a network device, something like that, which in itself might not be copyable or default constructible or something like that. Conceptually, single pass ranges only have one operation, and that is produce an item for me. And for single pass ranges, the whole iterator model is kind of artificial because like having plus plus and deref as separate things is not ideal. If you look at this example, it's the generator of string that says parse lines, so something like that. You can go over a stream and it would return a string for every line. In that case, the natural thing would be to return a std string PR value when accessing an element. But since it's possible to dereference the element twice, that forces the implementation to then cache the line somewhere so it's able to reproduce the same element again and again. We don't have time to discuss this in detail. Maybe just like remember, for single pass ranges, the whole operator plus plus deref thing is not the best solution. Before we come to the design decision slides, a small postscriptum. Not every range that generates elements is single pass. So if you have something like the repeat view, it generates one value until infinity, but it doesn't need to change state to be able to do that. So it's a multi-pass range. The same is true for iota. The iota view generates some number 0 to something. And because this state is tracked in the iterator and not in the range, it's also a multi-pass range. Okay, so most things that generate elements are single pass ranges, but there are some exceptions. Let's come to our design decision slides. Call this one minimal versus meaningful category concepts. The status quo in the standard library is that the category concepts are minimal. It means they only comprise the iterator category and nothing else. That, for example, implies that there is no bracket operator promised on random access ranges. It also implies no semi-regularity or regularity is promised for forward ranges, and also no const iterability. Pro arguments for this are that concepts can be composed, so they should be as small as possible. People will argue that if you want a concept that promises more things, you can always make that concept and put it on your functions and be happy. There's also the problem that if we say, for example, random access range requires the bracket operator, then we get into a situation where we might have a range that has a random access iterator, but not have the bracket operator. And what would that then be? Is that then a bidirectional range? So there's a trade-off to be made in this situation. These are arguments for having the concepts in the way they are. Counter-arguments are that concepts should be meaningful, and I think there is this general understanding that we don't want concepts to cover some properties of types, but we want concepts to mean something, like that they correspond to a certain use case. And if you have that mental model, then certainly random access ranges probably should have a bracket operator. The second design decision that is being made here is that we treat both single pass ranges and multi-pass ranges as ranges, although they are quite different. We have this, but we also have a clear way to separate them, because the single pass ranges are input ranges and the forward ranges are multi-pass ranges. So we have the ranges abstraction that covers both, but we have a concept to tell them apart. Pro arguments for this are that it's consistent with the iterator concepts that we had before. And there are several algorithms, like the find algorithm, that you can call on a single pass range or on a multi-pass range, and it will work. although, of course, the implications for single pass ranges are slightly different, because if you find an element in a single pass range, all elements before that will likely be gone. While if you find an element in a vector, you find the element in the vector, but it doesn't change the vector, okay? Counter-arguments to doing this are that other designs are more suitable for single pass ranges, and those other designs would prevent some cases of unexpected and even some cases of undefined behavior. Like if you are not required to call begin on a single pass range, then you can't call it multiple times and cause undefined behavior. But since that's the interface that we prescribe, that is the thing people have to use. If you're implementing algorithms, there's also some more complexity for handling these differences, but it's not relevant for most users. Let's dive into indirections and lifetime. Up here we have a std vector and a std vector pointer. And then we have certain actions, and I've listed what the semantics of these actions are. This is very standard C++, I think that everyone kind of knows, but it's good to see here. If you have a vector and you make it const, it protects the elements. If you have a pointer to something and you make it const, you just make the pointer const and not what it's pointing to. If you copy a vector, you copy the elements. If you copy a pointer, you just copy the pointer. If you compare a vector with another vector, you compare the elements. If you compare two pointers, you just compare the addresses. Destructing the vector frees the elements, while destructing the pointer doesn't modify the elements at all. Yes?
That is a typo on the first line.
There's a typo?
It's supposed to be vector of int pointers, not pointer to vector of int.
No, it's supposed to be... what do you mean?
Yes, standard vector of int and then standard vector of int pointer.
Yes.
A pointer to a vector, or do you mean a vector?
No, I mean in this case a pointer to a vector. If you compare pointers,
okay,
then you have pointer semantics. If you compare the thing itself, you compare the thing itself. So this is very trivial. There's no new hidden knowledge in this.
Those two things are also true if you have a vector of pointers. So like,
Yes.
except for the, I didn't see it look at the old one.
Yes, the destruction, and then you have the complexities. The complexities on the range on the vector are O of n, and on the pointer they're O of 1. Our ranges definition only covers the vector. It doesn't cover a pointer to a vector, okay? However, if we now look at the previously mentioned subrange, which is just a pair of integer pointers, could, for example, point to the begin of the vector on the left and to the end of the vector on the left, you will see that the semantics of this type are actually very similar to the pointer and very different from the container. Right? If you make the subrange const, it will not make the elements const. If you copy the subrange, it will just copy the pointers. You actually cannot compare the subrange. It doesn't have a comparison operator. And destructing the subrange leaves the elements that it points to untouched. However, in contrast to the pointer, the subrange is defined as a range. Right? That's what I said in the beginning. Containers are ranges, but also these shallow types are ranges. And that's something that a lot of people don't have internalized, is that the range concept covers containers, but it also covers types that behave like pointers to containers in a lot of situations. And the implications of this are such that if you have a function which accepts, I'm saying in this case a forward range because leaving the input ranges away makes this a bit simpler, but even in this case, you're accepting a range, and inside that function, you're creating a constref to the argument. Will that protect the elements or not? Is this even a range? I said before that the forward range concept does not imply constant durability. So there are cases where the result of that expression is not even a range. If we copy the thing, will it copy the elements, potentially allocating new memory? Or will it just copy a pointer Is this even well-formed? I said before that copyability is not a requirement for forward ranges. And finally, the comparison. What is actually being compared? Is it the elements? Is it an address? What complexity does it have? Is this even well-formed? As I said before, the subrange doesn't even have a comparison operator. So what you need to really store in your memory is that the standard library range concept make no promises regarding any of these things. Any and all of this happens in the wild. So if you have a mental model that says, I want to copy the thing, or I want to compare the elements, then you need to add a bunch of other concepts that make sure that your types behave this way. Design decision, making one abstraction for containers and indirect ranges, I'm calling them. Status quo is a range can have the semantics of a container or of a pointer to container. The usage patterns for this are identical. There is no dereference operator that you're calling, you just call begin on the thing, but in one case you're iterating over a container, in the other case you're iterating over this shallow type, the subrange. Pro arguments for this are, it's very easy to use. This abstraction, you can use a common interface for a vector and for a subrange of vector. It allows replacing these string references with string views, so it's a very, in some ways, intuitive concept. But it's also really easy to misuse, as I showed on the slides before. Const-correctness becomes very difficult to achieve because you don't know if the constness propagates to the elements or not. And performance implications, sometimes in cases like copies, are also unclear. This is one of the decisions where I've actually heard people in the committee multiple times say, maybe actually we should have designed this in a different way, that we have fundamentally different concepts for these two things. But yes, the ship has sailed. Lifetime issues. I'm returning back to this example I had before of the find algorithm. And I mean, everyone's favorite topic is lifetime issues nowadays because of Rust. And here we also have some lifetime issues. See, we can create a string down there, and if we pass the begin and end individually, it will pick the first overload, and everything is fine, right? This is what we've always been doing. This is clearly an indirection. We're passing iterators to the thing, we're not passing the thing. If we pass the the string, as an L value, that's it2, it will pick the second overload, and everything is fine as well. Now, if we pass a temporary of a string, what happens?
You get an iterator to a temporary object?
Yes. You get an iterator that is dangling. The thing went out of scope, and it3 is pointing somewhere. And that's, of course, something that we don't want. And a possible, I think I have it here, yes. First two are safe, the other one is R value and is dangling. A possible result of this analysis could be that we say, oh, R values are bad. We just need to prevent passing R values to that function. However, if we pass a subrange on S to the function as an R value, everything is fine. That's because the subrange is already in indirection. Like I said before, the subrange doesn't manage memory, so having this, passing the subrange as an R value is absolutely fine. And this means that the design decision that we reflected on before, covering two very different things through the same concept, makes it difficult to manage the situation. If ranges were always indirect, then the string R value would be prevented anyway. But since containers by themselves are ranges, we need to do something else. We could accept the argument as an L value reference up there. Maybe that's what Peter was getting at. And in that case, we would prevent passing R values, but we also prevent passing the good R value, the one that we want to be able to pass. we want to be able to pass a subrange of the vector. So taking an L-value reference, what the language normally suggests for this case, doesn't cut it.
But is this even a problem?
It is a problem because people, we want to be able to construct these lightweight ranges on the fly. We want to be able to say...
Yeah, but I mean, if you were specifically calling for something to find something in a temporary value, that's already a misuse of API. It should be straight obvious.
True. I mean, there are code guidelines, like the Google one, that says you shouldn't be passing things by reference to a function where you have a return value depend on the lifetime of that argument. It's true, but this is the way the standard library algorithms are designed, and we want to be able to pass this subrange because, like I said, you might be able, you want to do a string view. You might want to take only the first 5 elements.
It3, I just say the example with it3 is oh, what is the program I'm even looking for? Why would you?
Oh yeah. We want to prevent it3. That's correct. It3 is the bad example.
I don't see this as a problem because why would anybody write that?
Because people do. People copy stuff to functions and then get dangling iterators. The solution to this is the borrowed range concept that I've added here. And the borrowed range concept prevents the bad R value, but allows the good R value. And it's a very underrated concept, I think. We added it quite late. It's actually quite fundamental. And you should all probably be using it more if you work with ranges. A borrowed range is a range with reference semantics. That's kind of the easy hand-wavy explanation of it. And it covers L values and R values of ranges whose iterators can outlive the range. So in the case of the subrange, it covers both L values and R values because the iterators of the subrange, they're not tied to the lifetime of the subrange. But for something like a vector, it only covers the L value reference and not R values. So it allows passing an L value of the vector, but it prevents passing an R value of the vector. But for the subrange, it allows both L values and R values. So there's a small graph here, code painted. You have the vector, you create an iterator on the vector, and you have a lifetime dependency of the iterator on the vector. I think that's clear. If we create a subrange on the vector, we have a lifetime dependency from the subrange onto the vector. And this browser messes up my ASCII art. Okay. And then we have the iterator on the subrange, and this also depends on the vector, of course. However, this dependency is not transitive, it's direct. And that's what I meant up there with the iterators can outlive the range. There's no dependency of the subrange's iterator on the subrange. There's only dependency of the subrange's iterator on the vector up there. And this is exactly what the reference semantics are. If we created a reference at that point, there would also not be a dependency on the reference, only to the thing the reference refers to. So this is the borrowed range concept. It prevents lifetime issues. Pretty important. And
what's it implemented?
Hmm?
How can you distinguish these two cases?
Through an opt-in trait that I'm going to cover in a second. Okay, so we have one abstraction for containers and indirect ranges. A range can have the semantics of a container or of a pointer to container. In general, iterators depend on the lifetime of the range they were created from, e.g. for containers. But for so-called borrowed ranges, they don't. The pro argument for this is that it protects interfaces from lifetime issues, and compared to other range concepts that we have, the definition is quite clear, and I think the reference analogy also helps in understanding what this concept actually means, hopefully. Counter arguments to this are maybe we're just working around a previous decision that was flawed, mixing containers and indirect ranges. If we didn't do that, we wouldn't need this concept. It's also for people who are not very versed in concept territory, it might be surprising that a concept can evaluate to false on a type, but evaluate to true on a reference to that type. But that's the way our concepts work. They allow that. And this whole thing is based on an explicit opt-in trait. So if you want your range to be treated as a borrowed range, you need to enable borrowed range something something, set it to true. So I think it's not bad, but it's also not perfect. And we obviously cannot rely on the actual language mechanisms here. I think we're a bit behind the time. Range adapters. We're finally approaching the meat of the topic. First of all, terminology. A range adapter is a range that depends on or wraps another range. There are simple range adapters like std span, std string view, and std range subrange. Those are basically just pointers or just iterators or an iterator and a size. These are very simple. The only logic that they can do is denoting a subset of another range. No other real logic happens in these types. Then we have the composable range adapters, the ones I showed earlier, the transform view, the filter view, reverse view, all of these. They actually imply a lot of complicated logic that you can do. And then a lot of people don't list them here. I think actually they do belong in this topic, are the container adapters like stdq or even std flat set. They wrap a container and provide different patterns of insertions and removals. But in this very generic definition of range adapter, I think they also fit. In this broad sense, no implications arise for programmers from the term range adapter. There are range adapters that cover all the concepts or none of the concepts. Like I said, even something like the container adapter, in the end it adapts another range by name. The simple adapters in the first line, they have widespread usage in APIs, and I think people understand well how they work. And the container adapters, they're basically just used like containers, and you don't need to think about the adapter nature of them at all. The composable adapters are the most powerful, but they're also the ones that raise the most questions. And I've distilled 3 questions from these. Germans might recognize this. The big 3 question marks, I think, for range adapters are range adapters that cache the begin iterator, different forms of indirection, and the dilution of the view concept. Recall, this is the definition of a multipass range. Returns a forward iterator can be called multiple times, and complexity of calling begin repeatedly shall amortize to O of 1. Let's look at this last thing. What is that? Why do we have that? Look at this vector here, a bunch of elements. We're applying a filter on it for even elements, and then we're applying a reverse on it. The filter clearly means that if we call begin on the filter, we need to hop over these first 3 ones. So the complexity of begin on the filter is O of n and not O of 1. Right? Calling begin on the filter might parse the entire range because none of the elements might meet the predicate. I said it shall amortize to O of 1. Why should it do that? Well, let's look at views reverse. If we call end on views reverse, that calls begin on views filter. And so if we have a loop that looks like the loop down there, we would actually have O of n complexity every time end is called, and the whole loop would become quadratic in complexity. To prevent this case, the filter view needs to cache its begin once it has found it. And subsequently, the calls to begin on the filter view will be O of n, and that means the calls to end on the reverse will also be O of n.
You can specialize filter for bidirectional iterators.
Yeah, I mean, this is one of the popular examples. There are a bunch of other ones that you can construct, and in the end you will see that it's important that the range itself provide this guarantee and that you don't try to work around it from the outside. Just to summarize this here, calling begin on the filter needs to find the first even number, that's O of n complexity. Calling end on the reverse invokes begin on the filter. This would lead to quadratic complexity unless begin is cached. Strategies for caching. How do we cache? We can either not cache and just say we're an input range. Then we don't need to provide any guarantees. Like I said, the whole complexity guarantees we only need for multipass ranges. For some cases, this is okay, but it wouldn't work with views reverse because views reverse needs to call begin multiple times. And that's why if we make it an input range and not cache, you wouldn't be able to chain views reverse after it. The second possible strategy is caching the begin the first time begin is called. However, the implication of this is that calling begin now has side effects. These side effects are not observable because you can call begin again, and you will always get the same iterator. But it means that you cannot const qualify the begin function anymore, and then the range is no longer const iterable. We will look at that in a second. The third possible strategy is to cache on construction. Then you can keep begin as a const member function, but then you always pay the cost for finding it, even if you never iterate the range. This was a concern for a lot of people. And we want the adapters to be lazy evaluated, and if it potentially parses the entire range on construction, that wouldn't be very lazy. So the second is what the standard library does. We cache when begin is called the first time. So the property of the multipass guarantee changes to calling begin can be called multiple times, and it does not modify the range observably. It may modify the range in those cases. It's just that you cannot see it. You still see the same elements every time. What this means is, in this case, we just have a vector, we're filtering on the vector, and we're not able to pass that view onto a print function that takes by constref, because the filter view is not const iterable. This is the reason a lot of the range interfaces, or all of them, take things by ref and not by constref, because a bunch of the things are not const iterable. And this is very confusing for programmers because by definition, a multipass range doesn't change by iterating on it, but it actually does when caching happens. It's just that you can't see it. We're going to skip over these slides and go to caching begin. Status quo. Some multipass range adapters initialize a cache the first time begin is called. And we're skipping the second point. Pro arguments. It's necessary to cache begin for multipass ranges. There is no sane way to get around this. It's lazier than if we were caching on construction. If we cache on construction, we have potentially an OFN operation when constructing the range. The counter-arguments are that this weakens the multipass guarantee that would otherwise imply const iterability. So the mental model most people have is a filter on a container should be const iterable because we're not changing the container and also we're not changing the filter, but it's not because we have this caching that takes place when you call begin. The second topic, different forms of indirection. I've showed you this picture before. This is a borrowed range. Some adapters return borrowed ranges. For example, std views take returns a borrowed range. The iterator at the bottom does not depend on the view itself for its lifetime. But not all adapters return borrowed ranges. For example, the filter adapter, everyone likes hating on the filter adapter. The filter adapter is not borrowed. So if you have an iterator on the filter view, it depends both on the vector and also on the view. That's because the filter adapter stores much more state. It stores the functor, it stores a few other things, and people decided that they didn't want to put all of the state in the iterator, and that means that the iterator needs to have like a pointer that goes back to the range that it was created from. The implications of this are that if you have something like stdrange's min element, the function, which gives you an iterator to the minimum element in a range, and you pass it the thing at the top, views take temporary, this is well formed because the thing that is returned by views take is a borrowed range. However, the thing that is returned by the filter is not a borrowed range, so in this case also the iterator that is returned by the algorithm would be dangling, and this is prevented by the interface. In those cases, you can always create a temporary variable and then pass an L value to the view, and then it works again. But in some cases, this is ugly, and in some cases, you don't want to do this. Keep in mind, this is a design choice. We could decide to put all the stuff in the iterators, and then the iterators would be self-contained, and all indirect adapters would be borrowed. But the iterators become much larger. This slide just shows you that we have non-owning ranges in the middle that are not borrowed. Like I said here, the filter view is a non-owning adapter, but it's not borrowed. So, status quo is we have multiple degrees of ownership and indirection. Borrowed ranges are a well-defined concept, but not all adapters on L values return borrowed ranges. Non-owning ranges that are not borrowed are much more difficult to define, and we're not going to dive into that now. The pro-arguments for this is it keeps the iterators small. The counter-arguments is that it prevents using iterators standalone. Although using iterators standalone or returning them from functions is a common pattern also in the standard library. This again makes the mental model of what a view or an adapter actually is a lot more complicated because we have different kinds of owningness, non-owningness. The final point is the views concept. I asked ChatGPT, please summarize in one sentence how views in C++ differ from other ranges. This is what ChatGPT said. In C++, views are lightweight non-owning adapters that provide a window over existing ranges or containers without copying or owning the underlying elements, unlike other ranges that may store or own their data. This is wrong in many ways. If we look at views iota, this is not a range adapter, it's a self-contained range, but it's also a view. And if we look at the view number 2, we're passing an R value into the adapter, and this adapter takes ownership of the R value. And this is one of the most contentious topics, I think. You could probably do a whole presentation on this. We're just going to summarize really briefly. This is what view used to mean, semi-regular and copula O1, and both of these things were removed just post C++20 and applied to C++20 as a defect report. And this is counter to all the documentation that you had before on range v3 maybe, and this is also one of the reasons many programmers and ChatGPT get this wrong. The reason for this is some people wanted to be able to do this. Now we are able to do it, but we've further confused the mental model. Here, Eric Niebler, the original inventor of range v3, which is the basis for standard ranges, says that he is quite upset about this whole topic. You can read a lot about this on the internet. We're going to skip over this. The last design decision slide is views can now be owning in addition to be non-owning. This allows you to move containers into views, but it also means nobody except maybe 5 people in the world can actually explain what the view concept means. Summary. I think the main thing that we've seen today is that our core concepts, the range concept, the forward range concept, and the view concept all encompass more than they probably should. I think this is what makes having a mental model difficult, is that these concepts are too broad. Like a range can be something like a container, but it can also be something like a pointer to a container. A range can be something that is single pass, a range can be something that is multipass. For the ranges that are multipass, We're not even sure we can const iterate over them, although the definition kind of implies that we should be able to. And the view concept is just all over the place now. I think we could probably have had 80% of the features with 20% of the complexity, but this is C++. People always want to be able to do everything. Every possible use case needs to be covered, and that's why the whole thing is a lot more complicated now than it maybe should be. I'm sure if we had removed some of the use cases, there would also be people complaining that we've removed those use cases. All of that having been said, although the mental model is quite muddy for a lot of these terms, I want to close the presentation with this slide I had earlier and say they still work quite well in practice. Don't let yourself be distracted by my talk. If you use views in this way, locally in one function body to do one specific thing, then all of the stuff we were talking about today is completely irrelevant. You don't need to know whether it's const iterable or not, or what the level of indirection is, or whether something is copied or not. If you use views in this way, if you don't pass them on to another function, if you don't return them from your function, you're going to be pretty safe. And they're going to help you write code that is nicer than the code that you would otherwise be writing. And I think that concludes the talk. Thank you for attending. I'm open to questions. I also have a blog. You can check it out. Yeah, I also have a blog. I also have my own ranges library as a pet project. You can check it out. I've only recently made that public. It has some design decisions chosen differently from what the standard library did. And if you like to stay in touch, you can also connect on LinkedIn. But questions, first of all.
Maybe one or two.
Maybe one question. We have time for one, maybe.
Okay. Yeah, okay, just...
I was just wondering why the reverse example didn't override end. So it just had one of a different type. As you previously said, the sentinels could be at a different type. Was that not allowed for the forward iterator? So that way, if you had an end of a different type, you didn't need to call begin again.
The reverse... This one. The end of the reverse view could be a different type, yeah, but the operation still is. I mean, if you walk through a range from the end to the start, you need to always check whether you've reached the start.
Well, not if you... Well, then you just have to check, right, every time you de-iterate that you're beyond begin, because then you would sort of have to imagine an element after begin.
Yeah, exactly. I mean, you need in that case, you need to still begin somewhere to be able to check whether you've passed it or not.
Right.
So you can't get around to storing the begin somewhere. People have argued that the reverse should do the caching, but there are a lot of, this gets a lot more complicated if you connect more things that have different requirements. And there are, you cannot get around these complexity requirements. Just imagine the example I had in the beginning, where we have begin, and you call the bracket operator on the begin. Imagine begin did not have constant complexity, then invoking the bracket operator would also not have constant complexity. So we really need those requirements.
Thank you again.
All right.